So this is class note C in example 2.3 in lesson 2. In this problem, we are asked to solve this ODE with this initial condition. So this is an IVP, initial value problem. Now there's a star that I put here in this example, so there must be something that's tricky or complicated about this, and we will see that shortly. So let's start off by solving the ODE. We'll do that first, and then later on we will apply the initial condition. All right, so again, I've been encouraging you to classify ODEs when you meet them so that you know which technique we've developed might help to solve it. And in this case, highest order of the derivative in the equation is 1, so this is a first order ODE. And we can see that if I were to multiply here by y minus 1, I would eventually have a y times dy. That makes the ODE not linear. So this is a non-linear first order ODE. Again, it could be lots of things within that broad umbrella, but we see that this is already in the separable form. I have a function of only t divided by a function of only y, so that is actually the definition of the separable ODE form back from earlier in this lesson. Great, so this is a separable ODE, so let's solve it as such. So what can I start doing? Well, I'm going to try to put all the y's on one side. I'm going to multiply by y minus 1. And I'm going to keep the 2 with it. It doesn't really matter whether I keep the 2 there or leave it on the right-hand side. I'm doing that just so that the right-hand side doesn't have any fractions, like a 3/2 if I left a 2. So that's the right-hand side, dt. And then I'm going to integrate both sides. Great, so both of these integrals are actually pretty straightforward. So this is going to be 3t cubed over 3 plus 4t squared over 2 plus 2t plus c. And then, we'll simplify the fractions here in a minute. And then on the left-hand side, 2y integrates to 2y squared over 2. And then minus 2 integrates to minus 2y. Great, so I can cancel these, and I can simplify this to 2. And that gets me to y squared minus 2y equals t cubed plus 2t squared plus 2t plus c. Okay, tried to fit it in there. All right, so this is what we've gotten for the solution, but it is not solved for y. So that is part of the reason for the star in this problem, because solving this for y is a little tricky. So here's what I'm going to do, right? This is a very long expression, and I'm kind of too lazy to keep writing it. So I'm just going to call this a. So my new equation looks like this, right? Much simpler to deal with. So, in passing, this is something that I encourage you to do if you're just getting encumbered by trying to continue to write long expressions in your solutions or in any calculation you're doing. You can just replace them with something, maybe a letter, and that will help you, save your wrist from some writing. All right, so at this point, I want to solve for y. So what do? Well, I have a few options, but I'm going to take the most straightforward and perhaps scary of them, which is to employ the quadratic equation. So I'm going to recognize this as, or compare this quadratic equation to our usual form, so ay squared plus by plus c equals 0. And the quadratic formula there is what I'm going to recall. Here it is, so that we can solve for y. All right, so I'm going to use that here, and that tells us that y of t equals negative b. So negative b, so in this case, b is negative 2. So negative 2 is 2, plus or minus the square root of 2 squared, minus 4, a in this case is 1, and then c is this negative a. Okay, so there I am applying the quadratic formula in this context. All right, great. So what else? Divided by 2a. So again, a here, you can't see it, is 1, so that's just a 2. All right, so I have 2 plus or minus the square root of 4 minus 4a, plus 4a, because this negative and that negative multiply to a positive, divided by 2. And then I'm going to factor out a 4 in here, and the square root of 4 is 2 So that leaves me with the square root of 1 plus a in here. And finally, I can divide everything by 2 to get 1 plus or minus square root of 1 plus a. All right, so you can see why this has a star. So that was a lot of calculation. So bringing this back over here, we get that y of t equals 1 plus or minus the square root of 1 plus, and now I can plop in what a was back from over here. Great, so it looks like it was t cubed plus 2t squared plus 2t plus c. Great, so that is my solution for y. Now, the other reason this problem has a star is that, notice that I actually have two solutions. I have y equals 1 plus all the square root stuff, and y equals 1 minus all the square root stuff. And your gut should tell you that there should be a unique solution, right? So why do I have two in this case? Well, that's actually where the initial condition comes in really handy. So I'm going to look at the initial condition up here. It's y of 0 equals negative 1. So I'm going to go back up here and try to apply that initial condition. Before I do that, right, I'm going to think about which one of these two possible y of t solutions should be the solution. Okay, so I have y of t equals 1 plus square root of stuff, and y of t equals 1 minus square root of stuff as the two possibilities here. And my initial condition tells me that at 0, the value of the function is negative 1. So let's think about that, right? Because that immediately rules out one of these two possibilities. And which one does it rule out? Well, we have to think back to what square roots mean, okay? So a square root of a number is actually always positive, right? So I'll make a little public service announcement here in a minute. But because the square root of a number is always positive, then that means that 1 plus the square root of a number is also always positive. So there's absolutely no way that I could end up with a negative number for any of these y values in this specific solution. Okay, so that actually rules out for me this as a solution for this initial value problem. And again, that's part of what the initial conditions do for you. They allow you to write down unique solutions to the ODEs. Okay, so I'm going to use this as my form of the y of t, and I'm going to set negative 1 equal to y of 0, which is 1 minus the square root of, and then I'm going to put zeros in for t. So that becomes 0, that becomes 0, that becomes 0, and I'm just left with 1 plus c. So I guess I don't need a very long division square root bar here. Great, and this is equal to negative 1, so I'm going to subtract 1 minus 2 equals negative square root of 1 plus c, and then square both sides. 4 equals 1 plus c, and then solve for c. So c equals 3. Great, so then I put back in what my c value is over here. C is 3. So c is 3, and then I add 1, so that gives me 4. So my final solution is t squared. Oh, I just noticed that that t squared, I think, should have been a t cubed. Yes, that's true. So t cubed up here. So let's go back. It doesn't affect our initial condition calculation. So that's t cubed. Great. So going back down here, we have a t cubed plus 2t squared plus 2t, and then c plus 1 ended up being 4. All right, so this is the solution to the initial value problem, right? We get just one function, as we would have expected. Okay, so let me finish this by promising the public service announcement over here of the square root. All right, so you might have been used to thinking about something like, let's say, square root of 4 equals plus or minus 2, right? So you might have seen that in high school. But that's actually not true. Again, square root of x is always greater than or equal to 0. Anyway, I'll show you why that is in a minute. But let's talk about where this plus or minus 2 thing came from, right? So this probably came from your instructors having you solve something like x squared equals 4, right? And then they said, okay, so now you take the square root of both sides, square root of 4, and then you put a plus or minus because you should have two solutions. Okay, that makes sense in that context, but it's not that the square root is generating a positive and a negative solution. It's that you need a positive and a negative solution to the equation because it's a quadratic equation. So that has meant over the years that it's been very easy to confuse the fact that square roots should have only one answer, namely a non-negative number, with this plus or minus business. Okay, so if you don't believe me, not that calculators are the end-all be-all, but if you graph the function f of x equals square root of x, this is sort of the graph you will see. This is a graph that makes clear that there are no negative y values down here, right? So you do not get a graph that looks like this. Okay? And this is the other reason, the more mathematical reason, which does not require you to graph it using a calculator, why the square root of x result must be only non-negative. And you can see that from this graph. If there were a negative part to square root of x, then what would happen, right? If I drew vertical lines here, it would intersect the graph more than once. That would be a problem because if you remember back to pre-calculus, that would tell us that square root of x is not a function, right? Functions are such that when you graph them, they pass the vertical line test, which means that every vertical line drawn on the graph intersects the graph once, not twice as what happened down here. Okay, so that is another reason, and that's a much more calculator independent reason to believe the fact that indeed square root of x is a non-negative quantity. So we don't have square root of 4, for example, being plus or minus 2. That is a remnant of trying to solve quadratic equations that you may have learned back in high school. All right, so that is the end of my public service announcement, and I'll go back here and just put a star here that this was the solution to the initial value problem in this ODE. And again, the star was partly for, the star here was partly for all of this algebra that we had to do, but also because of the potential to run into some difficulty applying this initial condition, having obtained two functions for the solution to the ODE. And that's the end of this class notes.